In this section, we're going to look a little bit at the acidity and basicity of aromatic compounds. So first, starting with acidic aromatic compounds, let's look at phenol and benzoic acid. And we're going to compare these in relation to cyclohexanol. So there's cyclohexanol. Here's phenol. And here's benzoic acid. So we look at acidity in terms of pKa values. And the pKa of just an alcohol like cyclohexanol is around 16. Phenol is around 10. And benzoic acid is close to 4, just a bit higher. So with the acidity of these, remember that a lower pKa means more acidic. So of these three, benzoic acid is the most acidic. And also, hopefully you remember from Organic 1 that acidity trends can really be rationalized by conjugate base stability. So for all of these, if you react with a base, the base will come up here and take the proton, and then we get, just put a lone pair on the base. Now we get our conjugate base, and here our conjugate acid is BH+. So for all of these, if we react with some base, we can draw the conjugate bases of the acids. And just to do some comparison here, to see why we have these acidity trends, well, for cyclohexanol, the negative charge on the conjugate base, it has some stability because it's on the electronegative oxygen, but there's no resonance stabilization. And that's why of these three, it's the least acidic. Next, if we look at the conjugate base of phenol, we can delocalize the negative charge through resonance. And that certainly helps to stabilize that negative charge. We are delocalizing it over the 6 carbons on the aromatic ring. Then finally, with benzoic acid, we also have resonance stabilization. But here we're delocalizing over 3 atoms, and of the 3, 2 of them are oxygens, so that's why benzoic acid is the most acidic. Now, we can take this one step further and think about what happens specifically when dealing with phenol and benzoic acid derivatives. What happens if we have some other group on the ring? So these trends we're going to talk about can be applied to both phenol and benzoic acid, but just to keep it sort of concise, let's just think about phenol. And if we have some group on the ring, we react phenol with a base. We get our conjugate base, We still have this group on the ring. It could be at any position. So any groups that stabilize the negative charge, those are going to make phenol more acidic. Well, we know electron withdrawing groups stabilize the negative charge. So electron withdrawing groups attached to the ring will make for a stronger acid. If the group is an electron donating group, that's going to destabilize the negative charge. Which will make it a weaker acid. So let's just look at a few examples of different groups on the ring. Here we have an ethoxy. Let's do just phenol as a standard of comparison. And the nitro group. So of these, the nitro is a strong withdrawing group, and that makes this phenol derivative the most acidic. Then when you have a group like this ethoxy group, because of resonance donation here into the ring, that's an electron donating group. Essentially, you can think of this as sort of trying to pump more electrons into your already negatively charged conjugate base, so that's going to make it a less stable negative charge, and your corresponding acid is less acidic. So of these three, that's the least acidic acid. Now, as we already talked about, having a nitro group on the phenol ring is going to increase its acidity, but what about having the nitro group at different positions around the ring? So for example, here we have an orthonitro group, and here we have a metanitro group. In both cases, the best thing to do is analyze the conjugate base stability. So let's just think about the base coming over, taking the proton, and we'll draw out the conjugate base. Get O minus. We'll do the same thing over here. Now, what we want to look for as far as the stabilization factor goes is essentially seeing how close we can get this negative charge to the nitro group by resonance. So in this first structure, we can push these electrons down, and then through the ring, we can push those electrons over, these down, and this pi bond we can push over and put a negative charge on the carbon with the nitro group attached. So we get this resonance structure versus when we have the nitro meta, we can push these electrons around, but the closest you're going to get is one atom away from the nitro's carbon. Even if you try to draw another resonance structure here, we put the negative charge on this atom, that's not as good as getting the negative charge on the carbon directly next to the nitro. So that means having the nitro group ortho makes this more acidic. And you'll find if you did the same thing for the paranitro, you would be able to draw a resonance structure that puts the negative charge again directly next to the nitro group. In contrast to acidity, we can think about basicity when looking at the benzene derivative aniline. Here's aniline. The nitrogen has a lone pair. So if we react that with an acid, let's use HCl, that nitrogen will get protonated. We get NH3 plus, and Cl minus is our other ion. So the nitrogen in aniline is an organic base. Now what we can do now is think about having different groups on the ring. So we'll just put some group on the ring. And now, based on the identity of this particular group, we can think about the basicity of aniline, whether that group's going to make it more basic or less basic. If the group is an electron donating group, then it increases aniline's basicity. But if the group is an electron withdrawing group, it decreases aniline's basicity. So when dealing with an organic base, it's the opposite trend of the acid like phenol. So just to look at a couple of examples. Here is aniline with a donating group like methoxy. Versus aniline with a withdrawing group, such as this carbonyl. So the way to think about this is we're looking at aniline as a base, and that base is donating its lone pair to pick up a proton. Well, an electron donating group is sort of giving you an extra push of electron density toward the ring. That push of electron density enhances the basicity of that lone pair. In contrast, when dealing with an electron withdrawing group, because of its withdrawing nature, you can think of it as sort of having a pull of electron density. It's pulling electron density towards it, and that's also sort of causing this lone pair to be pulled into the ring, making it less available to act as a base. So this would be less basic.